All right, we're getting into MT6, and this is our first lesson, which is on perpendicular bisectors. And some of this is going to seem familiar because we talked about this with isosceles triangles. So we're going to be talking about perpendicular bisectors of line segments, and we're going to apply these to geometric methods to solve design problems using perpendicular bisectors of triangles. So here we go. Let me get your notes up so I have them in front of me. Perpendicular bisector is a line, a segment, or a ray that passes through the midpoint of a segment and is perpendicular to that segment. So if you've got a segment, like segment AB here, and you find its midpoint, there we go, and then you put anything, a line, a segment, or a ray that goes directly through that. Oh, that did not work. There you go, straight up through it right there. At a 90 degree, then you have created a perpendicular bisector, okay? Now, the cool thing about them is that any point that you put on there, so I'm gonna put a purple point right here. If you connect any point from these endpoints, A and B, to any point on this line, ray, or segment, so right from here to here, and from B up to here, say we name this point C, these lines will also be congruent to each other. And that is theorem 6.1. Okay? So the example they give, if CD is a perpendicular bisector of AB, then AC will be congruent or equal to BC. Okay? And then theorem 6.2 is the converse of that. If those point is equidistant from the endpoints of the segment, then it is a perpendicular bisector. So if you're able to prove that this is equal to this, it must be perpendicular and these must be equal. Okay? So that's what your converse is telling you. So let's look at example 1. We're going to use that perpendicular bisector theorem in just a moment here. All right, so find EF. And if we look at our diagram here, we are able to see that we've got EH here. It has been split in half by G, so that's our midpoint. And that FG is a line that is coming through at a 90 degree. So it is a perpendicular bisector, which means that EH, or EF, and FH are equal by the perpendicular bisector theorem. All right, so our fill in the blanks down below tell us then that EF must be equal to HF. We can then set these values equal to each other. So there's your fill in the blank. 4A minus 15 will equal A plus 12. Look how we substituted that in for those values. EF equals HF. And then we're going to solve. A equals 9. So yes, our values that we're filling in. There we go. Now, we were not solving for A. We were solving for EF. So we're going to go plug in that 9 into the equation and find out that it is actually 21 units long. All right. Now, you go ahead and solve this, and then come back and check. All right, did you get that RT is equal to 13? All right, let's go on to example 2. So now we're going to use the converse. Now if we look at this guy, we can see that this WX is equal to WZ, 25.3, and that it's at a 90 degrees. that means that these must be equal as well. And they're asking us how big is xy? Well, if this is 22.4, this must be 22.4 as well. And that's what they're going to tell us down here in words. So they're going to write out a whole proof for it. By the definition, I'm going to start down here. By the definition of segment bisector, xy will equal zy. Because zy equals 22.4, xy will equal 22.4. Okay. Now you go ahead and do this one, and then check it. And did you get that wy equals 3? I hope so. Okay. Now, this one's kind of cool, guys. I'm excited about this. When 3 or more lines intersect at a common point, the lines are called concurrent lines. The point of intersection of concurrent lines is called the point of concurrency. A triangle has 3 sides, so it also has 3 perpendicular bisectors. These bisectors are concurrent lines. The point of concurrency of the perpendicular bisectors of the sides of the triangle is called the circumcenter of the triangle. Okay. So here's the theorem we're going to work with. The perpendicular bisectors of a triangle intersect at a point called the circumcenter that is equidistant from the vertices of the triangle. And I'm going to show you this in a different software, so just hold on one second. Okay, so going into this equation, or into this software, this is actually called Geometry. If you ever want to download this, you can go to Manager. And I've made myself a triangle here. And what I'm going to do is I'm going to go down and find the perpendicular bisector option, and I'm going to make one on the side of each side of this triangle. Okay. Now notice, this is just so super cool. I'm just super nerding out, but I'm going to put a point right there. Look at that, point D. That's your point of concurrency. That is the circumcenter. And if I grab any of these points, I'm going to grab point B right now, and I'm going to drag it around. You'll notice that point D will still stay connected with all 3 of those lines. Those perpendicular angles at the midpoints always meet up. Now, if I create A as an obtuse angle, it forces D outside of the triangle. Notice that. It's going to push the circumcenter outside of the triangle, opposite that obtuse angle. Okay? If I make them all acute angles, it keeps it inside the triangle. If we see D right on the triangle, then the angle that it's across from, so in this situation, C is the angle it's across from, C would then be a 90-degree angle. So that's kind of cool. Wherever that circumcenter is, tells us something about the angles in the triangle. Huh, that's kind of cool. Next and last, one thing I want to tell you, circumcenter actually stands for something. Circum means around or about, and center means, in the middle. So about the middle. So what they're trying to tell us is that this point D is in the middle of a circle, and the circum means it's going to go around this triangle. We're going to make a circle that will perfectly go around this triangle. So watch what I'm going to do. Let's see if I get my tools. My son would really like some help with math right now, but he's going to have to wait for one more second. Hold on. So I'm grabbing my circle tool. I'm going to put it right at D, and then I'm going to hit any one of these vertices, A, C, or B. Look at that. Point D, our circumcenter, is perfectly between all three of the vertices, and it doesn't matter where I move them. That is so cool. All right, I'm gonna help my son. I'll be right back, guys. All right, now we're going back. Okay, so here it is. The other thing you need to see in here is that, and it's very elegant. It looks a lot cooler in here. Here's the circumcenters, and they aren't all like tons of lines like in mine where they like extended out beyond there in lots of ways. Look at this. It makes 6 right triangles. So here's a right triangle that perfectly matches this one, by the way. Look at that. Because if you look at it, this and this are the same. These are the same distance, and this is reflexive. So those are 2 exactly the same right triangles, okay? And remember, all of these are going to be exactly the same length because they're equidistant. They're all the radius of that circle. Radius of the circle. There we go. Okay? Now, these will be the same as each other. These are going to be the same as that one, and these will be the same as that one. So you can't, like, they're not all exactly the same as each other every way around, but it's pretty cool. Okay, so let's look now. They gave us some information. BF, find BF. So they want us to find BF. So I'm going to get rid of this right here. Sorry about that. I want us to find BF. I'm going to put an X there. If D is the circumcenter of ABC. So AC is 9. So I'm going to write down that AC is 9. DE is 1.83. And DF is 1.53. Okay. So we need to find BF. And the question we have to ask ourselves is, how would we find BF? Well, BF is part of this triangle right there. Okay? So if I look at that triangle, I'm going to draw it out here. It goes BF. There's an X there. 1.53. I still don't know. This is a D here. There we go. I don't know what this one is. However, I know it matches with this guy and this guy. So maybe I can solve one of them. So let's go down here. I'm going to look at this triangle. I know that I'm going to draw that one out. Let's see. Hmm. 1.83 E, C, and D. And this one will be the same as DB. All right. And this one is going to be 9 divided by 2 because AC gets split in half. So 4.5 and 4.5. So that's going to be 4.5. All right. And now I can solve that because it's right triangles. Right triangles, guys. We can do that. We can solve it because of the Pythagorean theorem. So they've solved that out. Here we go. Here's the fill in the blanks that they gave you. EC is half of 9, or 4.5. All right. And then we're going to use the Pythagorean theorem to find that DC. So DC squared is going to equal 1.83 squared plus 4.5 squared, which is going to equal 23.6. which is about 4.86. Okay, so now we know what DC is, and DC is the same as DB or BD. Now we're going to substitute that into the other triangle that we were doing up there. Okay. By the circumcenter theorem, we're going to plug that in, and here we go. 2.34 plus BF squared equals 23.62. BF squared is going to equal 21.28, which will be about 4.61. Now take some time to work that out. Try that on there. Figure out what we just did in there. Pause it, look it over. Okay. And now try it here. These are definitely going to be problems that you're going to get in ALEKS, so feel comfortable with them. So go ahead and try this one. Come back and see how you did. Did you get 1.7? Okay. Now, if Alonzo wants to install a fountain in his triangular garden, where should he place the fountains that's equidistant from the vertices of the garden? Okay. So if he's got those vertices, where should he place it so that it is exactly equidistant? Okay. Now, they went ahead and wrote it out for you. Use a compass and a straight edge to construct the perpendicular bisectors. So this is where we do constructions, and you're going to have those in ALEKS. And remember how we did those in ALEKS, where you have a segment, a segment, and from each end, you go ahead and make a swoop the same length from this one, and then from this one, and then there you go. Nice perpendicular bisector. You're going to do that from those points. And then from these 2 points, and do that. And you only have to do it from 2, by the way. You don't have to do it from 3. Okay. All right. Now you can go ahead and try that yourself. You don't necessarily need to, though. Go ahead and try it in ALEKS.